All right, in this video I want to take a look at some special cases so that you'll recognize them when you get there. So suppose we started with a system, we made the augmented matrix, we um, put it in row echelon form, got to here. This bottom row here is a real tip-off because this bottom row corresponds to the equation that 0 equals 1. Okay, I don't care what these equations are up here. The only way to make this system solved, in order to find a solution to the system, is find a way to make 0 equal to 1. Well, there aren't any values of the variable where 0 is going to equal to 1. So when you get down to something like this, that tells you that you have no solutions. I'm really hoping the new pen comes in soon. No solutions. So that's one of the special cases. Suppose you had a very similar problem, but the augmented matrix came down to something that looked like this, where this doesn't have 0, 0, 0, 1, it has 0, 0, 0, 0. So that is an equation that is just fine and dandy. There's no problem with having 0 equal to 0. So everything up here is what needs to be satisfied. So what are we looking at? We're looking at 1x. So I've got x plus 2y plus z equals 3. And I have y plus 4z. So I'm going to do this, plus 4z equals 0. When I see something like this, I see only two leading ones, but we had three variables. Okay. The columns that have leading ones correspond to variables that we'll call leading variables, and the column that doesn't have a leading one, there is a 1 in the column, but it's not a leading one. This was the leading one in that row. This column corresponds to the third variable, and we're going to call that a free variable. That's the thing we're going to be able to let be anything we want, and then these other two are determined. The thing is, we really could, any one of them could be free, and the other two are determined. But because of the fact that there's ones here, it's really easy to solve this first equation for x, right? This is x equals 3 minus 2y minus z, and likewise, this one is really easy to solve for y. Y equals negative 4z. So the z is the free variable, and then we can solve for that too. Actually, this one, when I plug this into there, let me do that. I'm going to plug the y into here. So I've got x equals 3 minus 2 times y, but y is negative 4z. That's a 4. And then a minus z. So x is equal to 3 minus, let's see, that's plus 8 minus z, so minus 7z. So I have y expressed as a function of z, I have x expressed as a function of z. Z is a nice thing to be the parameter, right? What just happened there? So what I have is I can say that x, y, z is equal to 3 minus 7, I'm going to, instead of z, I'm going to use a parameter, let's say t. Y, which is negative 4 times the parameter t, and then z is just t. So for any choice you make, whatever you let z equal to, choose a value, t, then y is calculated, and then x is calculated, and you've got a solution to this system. What you've just described is a parametric representation of a line in three-dimensional space. For every value of t, you've got a point x, y, and z, so you're describing some line. You're looking at the intersection of two planes. This is the line. Okay? So solving that system of equations doesn't give a unique solution. It gives infinitely many solutions, and you represent it parametrically. Okay? Now, one more special case here. Sometimes you get there and you have more than one free variable. So for instance, here was this, we started off somewhere with a system of two equations and four variables. We made the augmented matrix, we bring it down to row echelon form. In fact, in this case, I went down to a reduced row echelon form just to make my life a little easier. So what I have here is I have two leading variables, right here and here, and I have two free variables, right there and there. Right? So what I'm going to do is I'm going to solve for my leading variables in terms of my free variables. This first equation is x plus 2y, so I'm going to do x, y, z, and w, I guess, plus 3w equals 4. Solving for x, x is, that's supposed to be an arrow, arrow. X is 4 minus 2y minus 3w. Likewise, in the bottom here, I've just got xy, so z plus 2w equals 1, which is easy enough to solve that z is 1 minus 2w. So my two leading variables, x and z, the first and the third variables, I now have expressed in terms of y and w, the second and the fourth ones. So here we go, x, y, z, w. I said w, didn't I? I thought I did. But I wrote a z, so x, y, z, w equals x is 4 minus 2t minus 3s, so I'm using t for y and s for w, so t is in the y place, z is then 1 minus 2 times w, which is s, and then w is just s. So my two parameters now, this one was t and this one was s, and I expressed the other two variables in terms of it. What I have described now is out in four-dimensional space, I've described a plane. I say four-dimensional space because I have four variables, and the plane because I have two free variables. I have two parameters here, s and t. So anyway, there's situations you might find yourself in as you're doing Gaussian elimination or Gauss-Jordan elimination, when you have potentially no solutions or infinitely many solutions. And when you have infinitely many solutions, you can describe the whole solution set by using a parameter, and if you have it in either row echelon form or reduced row echelon form, it's in fact reduced row echelon form is the easiest. You express the leading variables in terms of the free variables. And there you go.